We're back. We're back to talk about some eigenspaces. All right. So we're moving up in the world. Now I have a 3 by 3 matrix. Now, what I forgot to mention in the beginning is that our eigenvalues and eigenvectors only apply to square matrices. Does not apply when we're talking about any other size matrix. It has to be a square matrix. Fun caveat. All right, so we're going to find a basis for the corresponding eigenspace for our eigenvalue of 2. So we're not finding eigenvalues yet. We're still working on that. We'll work up to that. Right now, we're just being told what the eigenvalue is, and we're being asked to find the eigenspace, and from the eigenspace, find a basis for that. Right? Now, just to remember, so an eigenspace is a subspace of, in this case, R3. Right? So this is in R3. So our eigenspace is going to be a subspace of R3. And our eigenspace is the null space of A minus lambda I. Right? So what that means is if I solve A minus lambda I x equals 0, right, the vector, the parametric vector form creates the basis, the vectors in the parametric vector form create the basis for the null space of A minus alpha I. Therefore, it's the basis of the eigenspace. Ta-da! Right? And now remember, so this happens because, remember, our basis has to have linearly independent vectors in it. And by definition, the null space is all solutions to this equation, right? The null space was always every solution to AX equals 0, or that homogeneous equation. Now we're adding that little like caveat of A minus alpha I, or minus lambda I, not alpha. So by definition, the vectors that come out of that parametric vector form are always going to be linearly independent, right? Because we're listing all of our free variables, and our free variables have no interaction with each other. So the vectors that are formed are based on the free variables, and they're just kind of like doing their own thing, right? So that will always be the basis for that space. And that's just where we're going with this. All right, so to start off, first thing we need to do is we need to figure out what our A minus lambda I matrix is going to look like so that we can actually augment some stuff. So our A minus 2I is what we're going to set up first, which really just means that all I'm going to do is on the diagonal here, I'm just going to subtract 2 from each of those entries. Everything else is going to stay the same. So my A minus 2I matrix is equal to 2, negative 1, 6, 2, negative 1, 6, 2, negative 1, 6. Well, that's fun, right? Hopefully, without even needing to do any augmentation and like thinking about this, right? Each of my rows is the same, which means that I'm going to have 2 free variables. Right, and I can get this down very quickly to 2, negative 1, 6, 0, and zeros everywhere else. And then just for fun, if I divide this top one by 2, it's going to get me down to, I'm just trying to get x1 by itself, just for, so 1, negative a half, 3, 0, and the rest of it, whatever. So in parametric vector form, this is telling me that my x1, x2, x3 vectors, or solution vectors, are always defined by x2 times the quantity a half, 1, 0, right? It's 0 because x3 is free, so x2 has nothing to do with x3. x2 and x3, so x2 and x3 are both free variables. And x1 is defined in terms of both of those. So x3 would be -3, 0, 1. So our basis for the eigenspace corresponding to lambda equals 2, or our eigenvalue of 2, is the set 1/2, 1, 0, and -3, 0, 1. Okay? Each of these independently would create their own line. So the span of those two things is like a whole hell of a lot of stuff. And the span is all of R2, but we don't care about no, the span is not all of R2 or all of R3, but it's two different lines. And those two different lines, it might be all of R3. Nope, can't be. Not enough vectors for that. Okay, ignore me. Here's my basis. There we go. Okay. Now we're going to make use of some really, really exciting things, and that is our idea of triangular matrices. So remember, a triangular matrix is anywhere either everything above the main diagonal or everything below the main diagonal is all zeros. And if we take this idea of A minus alpha I, and we take the idea, if you remember, that the if I have a triangular matrix, the determinant of a triangular matrix, oh goodness, let's make that better, of a triangular matrix is equal to the product of the diagonals. Now, if I have a triangular matrix, then the eigenvalues are just the numbers on its main diagonal. And the reason for that is, if you think about the fact that that in order for us to not have a trivial solution here, then that means that A minus lambda I needs to not be invertible. And for it to not be invertible, one way to talk about that is to say that the diagonal is equal to 0, okay? Or that the determinant is equal to 0. So if the product of my diagonals equals 0, easy to see that if I have this minus lambda, well, one way to make that equal to 0 is to let lambda equal whatever that A11 is. Same thing here. That would be 0 as long as lambda is equal to A22, and so on and so forth, right? So if our determinant is going to equal 0 in a triangular matrix, it's just the products there, and then that automatically means that the values in our main diagonal are equal to our eigenvalues. Hope you followed. All right, so here's what we're going to do. So we're going to do a lot with these two matrices. So first, we're going to talk a little bit about what the eigenvalues of each of these are. And we're not going to go too and they're triangular matrices, which is beautiful. Okay? We'll talk a little bit about multiplicity of eigenvalues. We're going to talk a little bit about this 0 eigenvalue, because wait a minute, that doesn't make any sense, because if 0 is my eigenvalue, isn't that a trivial solution? Maybe, maybe not. And we're going to talk a little bit about how to find the eigenbasis for each of the corresponding eigenvalues. So in this case, I'm going to have possibly 6 different bases here that represent the 6 different eigenspaces that I might possibly have for these 6 different eigenvalues for these 2 different matrices. Say that 6 times fast. So we'll focus on A first, and then we'll focus on B and think about like what the hell's going on here. All right, so for A, so because this is triangular, that means that all I need to do is look right here to figure out what my eigenvalues are. So this tells me that for A, I have 3 eigenvalues. So I'm gonna label them. Lambda 1 is 3, lambda 2 is 0, and lambda 3 is 2. So what I'm going to do is, so we're good. We found our eigenvalues for those. Now this one is a curious beast. And we're going to take a little side note here to talk about this curious little beast. And that as long as A is not invertible, then, so this would imply, so here, side note, when for lambda 2 equals 0, we're trying to show that alpha, or that A times X is going to equal lambda times X, right? So if I think about lambda 2 equaling 0, what we're saying is that A times X is going to equal the 0 vector, right? Because 0 times any vector is the 0 vector, which is just our homogeneous equation, right? And what we've proved is that if A is not invertible, then this has a non-trivial solution. So the fact that 0 is an eigenvalue is not an issue, right? So 0 being the eigenvalue does not automatically mean that our eigenvector equation, or that this equation here has a non-trivial solution. It has only the trivial solution. So it also has to do with the fact that A is not invertible here. So, okay, where are we at? Okay, aside. So let's find our matrices for each of these. So what we're going to do, so each of our matrices, we're going to then do our RREF. We'll find our different, find our parametric vector forms, and those parametric vector forms, those vectors are going to represent the basis for that eigenspace, for that eigenvalue. So for lambda equals 3, I'm just going to take 3 on this matrix. I'm going to do 0, 6, negative 8, 0, negative 3, 6, and 0, 0, negative 1. All right, and I'm going to augment that with 0, 0, and I'm going to let you do that on your own. So I want you to finish this. So come back, and we'll do the same thing with these other two vectors, or other two. So lambda being 0 gives me just A, right? If I'm not subtracting anything, if I'm subtracting 0, then it doesn't matter. Now you could just row reduce this, right? Because because the 0 vector over there doesn't change anything. All we're looking for is whether or not we have some kind of a, we're just kind of looking for the relationship between our free variables, but it doesn't matter. So this one would be 1, 6, negative 8, 0, negative 2, 6, 0, 0, 0. All right, so should make sense that in each of the pivot points, or in each of the corners, if it's a triangular matrix, that are, because these are defined as our eigenvalues, that each of these matrices is going to have a 0 in the position where that eigenvalue was originally. Hopefully that makes sense. All right, so pause now, do RREF, write out and see if you can come up with what the basis for each of these eigenspaces would be. Come back in a minute. How'd you do? So each of these bases have a different eigenspace, or a different eigenspace. So that should be a 1 down there, okay? And you'll see that they're all just a little bit different, right? And each one has its own corresponding basis for the eigenspace, or each one has its own corresponding eigenvalue. So we found all the eigenvalues here for A, and all the eigenvectors, excuse me. All right, now for B is an interesting one. So for B, you'll see, if we look along this main diagonal, again, this is a triangular matrix, so excuse me. something caught in my throat. So I have lambda 1 is 4, lambda 2 is 1, and lambda 3 is also 4. So you'll notice that I actually have the same eigenvalue. So what that means is that the eigenvalue of 4 has a multiplicity of 2. So what that means is that it's that we treat it twice, right? Has multiplicity. And the best way to describe this is thinking about, and this will make a little bit more sense about why this is true in the next section. But if you think about the fact that I have a 3x3 matrix, right? In a 3x3 matrix, there's really only going to be 3 different eigenvalues. Well, we're going to explain this in the next section. We'll talk about this. So keep thinking about why this would make sense that alpha, or that an eigenvalue of 4 has a multiplicity of 2, and then altogether we end up having 3 eigenvalues here. I just happen to have one that's the same multiple of each other. So what that means is we really don't have to worry about lambda 1 equaling 4 and lambda 2 equaling 1 in terms of finding our basis. So pause now, find the bases for those two, and come back in just a second. Ta-da! All right. This was just a fun adventure in finding null spaces over and over and over again. Hey! Yeah. All right. This last theorem says that if V1 through Vr are eigenvectors that correspond to distinct eigenvalues of lambda 1 through lambda r of an m by n matrix, then the set V1 through Vr is linearly independent. Right? So as long as those eigenvectors correspond to a distinct eigenvalue, then that set is linearly independent. So if you notice here, if we think about the sets that make up, or the vectors that we've gotten, so this vector, and this vector, because they correspond to distinct and different eigenvalues, those are all linearly independent. Same thing over here. This one and this one are linearly independent because because the two of them do not share an eigenvalue. Now this basis here, it applies to a multiplicity of 2 for our eigenvalue, but it's not linearly independent with itself. That should be a duh. So anyway, the eigenvectors that you get out from your eigenvalues are going to be linearly independent. Ta-da! All right, in the next section, we're going to talk about actually how to find our eigenvalues. Yay!